afternoon, everyone. I hope you can all hear me clearly. It is a great pleasure to join you virtually at International Conference ICAST 2025. My name is Hassan Bashir from Dilla University, together with my co-authors, Mr. Wandimna, Dr. Tafarra, and Dr. Tasaw. I am delighted to present our research title, Performance Enhancement of Distribution Network by Optimal Placement and Size of Renewable-based Distribution Generation in the case of Jigjiga City 50 kV feeder. I would like to express my appreciation to the conference organizer for giving us this opportunity and to all participants joining from different places. So without further delay, let us begin the presentation. Here is the outline of the presentation. Start from introduction, research gaps and contribution, description of the case study area, methodology, result and discussion, finally the conclusion and the future work. When we start from the introduction part, electric power system consists of three basic components, that is generation, transmission and distributions. Then the distribution networks are responsible for delivering power to the end users while maintaining reliable and quality powers. However, radial distribution systems may face higher power loss, poor voltage regulation, and low reliability, particularly in developing countries like Ethiopia, where the network infrastructures are aging and demand is rapidly increased. To address these challenges and to meet the growth demand, integration of renewable DG is a particular solution. And DG units such as PV and wind are a small-scale decentralized source installed near the load centers. And one of the basic consideration to be integration in the DG is its location and size. Optimizing this location and size. Otherwise, the benefit is reduced. So, optimal location of DG may give to reduce technical loss, enhance voltage stability, and overall system performance improvements. DG refers to the production of electricity near to the point of consumption using small-scale energy systems such as PV and wind, rather than in centralized power plants. And integration of such renewable DG have technical and economical and environmental benefit. When we see the technical benefits, it reduces loss, enhance voltage stability and voltage profiles, and improve reliability. While the primary task is supplying energy, based on the capability of delivering active and reactive power, DG can be classified into four groups, type 1 up to type 4, so look like this. The next part is research gaps. So many researchers can do a lot of research regarding to this area. However, most study focused on single objective optimization, mainly real power loss reduction, without considering reactive power loss, reliability and cost-benefit analysis, and several works optimized only DG location rather than both location and size, and often lacked compressive system constraints. And many studies use standard test systems, that is IEEE 33 and 69, instead of using real distribution systems, which is limiting practical applicability. Our papers aims to bridge the existing research gaps through the following contribution. Here is a contribution. The first one is formulate multi-objective functions and use real 85-bus distribution systems and analyze the impact of the number of DG and compressive cost-benefit analysis. Here is the description of the case study area. As to look like the diagram, the single line diagram of the Jigjiga distribution, Jigjiga substations. It can get from Harar and it has 4 50 kV and 4 33 kV buses, and our study focused on L4 of line 4 of 50 kV buses. When we see the solar potential resource assessment, in general, Ethiopia estimated solar radiance is 4 up to 6, and when we see specific in Jigjiga, it ranges from 5.86 to 6.5, and the monthly solar radiance, average solar radiance looks like in these diagrams, and the annual average is 6.12. Here is when you see the meteorology part, it starts from data collection and the data analysis, and then system is modeled within Visio and MATLAB, and the existing performance analysis using load flow analysis, then model DG and apply PSO, final performance analysis after integration, and finally compare result and make conclusion. The data is collected through different methods: interview, direct observation, and secondary data, and the collected data are those data are collected. Here is a single line diagram of the 50 kV feeders. It has 85 buses, and total length covered is 52.1 kilometer, and the total load demand, active and reactive load demand, such a figure. When you see the optimization problem, a load flow analysis is in fact bread and sugar for any power system engineers, gives the pulse of the system, and the equations are use a lot of equations as look like here. And when you see the objective function and system constraint, the PSO is used for optimization, and it has so many inputs: that initial input data, load line data, and load data, and the objective function, which is the composition of three objective function, and there are two types of constraints: distribution line constraint and DG constraint, and give optimal output result, which is location and DG size. Here is the flow chart of the PSO algorithm for optimal placement and the DG units. First, the position representation are represent such like that, and position and velocity are updated for each iteration. When we see the result and discussion, the simulation analysis was taken by MATLAB softwares, and there are 5 cases for analysis: case 1 up to case 5, and the case 1 are base case or existing systems, and case 2 are single DG integration, 2 DG integration, 3 DG up to 4 DG integrations. Let's see the case 1, which is existing cases, and the voltage profile for the 85 buses look like this, and 54 buses or 63.53% of the buses are below the standard or voltage level. That means according to IEEE 5047, minimum voltage is 0.95 and maximum is 1.05. And the minimum voltage is occurred in bus 83, which value is 0.9116 per unit, and the branch power loss look like such figures, and the total power loss is 476.23 kilowatt. Case 2, that means integration of 1 DG, the voltage profile is enhanced from the existing. The red line indicates the voltage without DG, then the blue one is the voltage with 1 DG. It has a big enhancement. That means the minimum voltage is raised from 0.9116 to 0.976, and it reduced total power loss by 281.206 kilowatt. When we see the case 3, the voltage profile is enhanced as such like that, and the minimum voltage rise from initial case to 0.98 per unit, and the total power is reduced by 393.955 kilowatt. In case 4, the voltage profile also enhanced, and the minimum voltage rises from 0.116 to 0.992 per unit, and the total power is reduced by 440.1.37 kilowatt. And when you see the last case, case 5, integration of 4DG, the minimum voltage increases from 0.116 to 0.114, and the total power loss is reduced by 456.37 kilowatt. When you see the summary of the simulation results for DG placement and size, it has 5 cases, and the performance indicator are power loss reduction and minimum voltage. The power loss is in kilowatt and percentage, and DG locations are its location, bus number, and the size in kilowatt. When you see this figure, it represents the percentage reduction from base case and the total real power losses. In base case, the reduction is 0, it is initial or the reference one. When you see 1 DG integration, it is 59% reduction, and integrating 2 DG gives 82.7% reduction. When you integrate 3 DG, 92.7% reduction, and 4 DG, 95.8% reduction. However, the total DG size of case 3, case 4, and case 5 are such a figure, such amount of kilowatt respectively, and 3 DG and 4 DG saved for 47.42 kilowatt and 62.42 kilowatt respectively compared to 2 DG, while 1147 kilowatt and 1328 kilowatt extra needed than 2 DG. That means 2 DG requires less amount of DG values, so that selecting 3D, selecting those cases, that means case 4 and case 5, as a best case is not economical when we compare its benefits. When you come to the cost analysis and payback period, after proposing a solution, economic feasibility is a basic step. So in base case, the power loss is such amount of kilowatts, and annual cost is above 10 millions, and using electric tariff 2.42 kilowatt hour. After disintegration, the power loss is reduced, and cost loss cost is above 80 million, and installation cost is such amount of burr, and when you exchange 1 USD, and the average installed cost for fixed tide utility scales is 1.28 watts, and finally the payback period is 6.04 year. When you come to the conclusion part, reliable power system is crucial for economic and social growth. This study focused on voltage instability and power loss reduction in Jigjiga, feeder 50 kV feeder 4, using optimal placement and sizing of solar-based distribution generation with incorporation of multi-objective PSO, and the optimal solution is 2 DG, that means 1.826 megawatt at bus 26 and 58, and power loss reduction is 82.7%, and the voltage improvement from this to this, and payback period is 6.04 years. Adding more DG slightly improve performance but reduce cost effectiveness. So 2 DG configuration was the most efficient and cost effective solution is a final conclusion. When you see the future work, in the future researchers can conduct dynamic load and time varying simulation, and integrating energy storage systems, as well as techno-economic and life cycle assessments, or study policy and regulatory framework to enhance renewable DG adoptions. Thank you all. If you have any question, we are welcome.